Yes, it's a pleasure to introduce today's speaker, Professor Hermann Lüehr. Hermann has had a long and highly successful career, not just in magnetometry, but also in leadership. Hermann was the PI for the image ground magnetometer array, the magnetometer on AMPTI-IRM, the magnetic field investigation on CHAMP, and he is the co-PI for ESA's swarm mission. For his many contributions, Hermann became a fellow of the AGU in 2010, and he then received ESA's Julius Bartels Medal from the EGU in 2011. His interests include geomagnetism, magnetospheric and ionospheric physics, instrumentation, and current systems. And it's current systems that he will be discussing today. Before we begin, I'd like to remind you that this presentation is being recorded. Please keep your voice on mute during the course of the presentation. If you have any questions, please enter them in the chat box. I'll be happy to ask them at the end of the presentation. And now let's begin. Professor Lüehr, please proceed.
Yeah, many thanks, David, for the kind words of the introduction. And I also like to thank the organizers for giving me the chance to speak in this online seminar. So let me see, now here we are, full screen, yes. Oops, why doesn't it? Okay, it works like that. Yeah, the outline of my talk is I'm starting with a historical background and then come to the general characteristics of the field-aligned currents, the scale dependence of field-aligned currents. I will also touch the measurement techniques of field-aligned currents because this may be interesting for some younger scientists. Then I show some storm features of the FACS, and in the end I will focus a little bit on the small scale field-aligned currents, which I find particularly interesting. Yes, you cannot start a talk about field-aligned currents without mentioning Christian Böhm. He was really a visionary. His famous Terrella experiments, there he was shooting cathode rays onto a magnetized sphere, and what he found was that the electric currents are guided by the field lines to a ring around the poles. And in reference to these early experiments, the field-aligned currents are also often termed Birkeland currents. And for me, particularly interesting was a figure from his book in 1918, where he was showing the pairs of field-aligned current going up and down. And beneath the field-aligned currents, he was already predicting a horizontal current in one direction on the one side and in the other direction on the other side. That means he was already predicting the electrojets at that time in connection with the field-aligned currents. Yes, but after him, there was a heated debate about the existence of field-aligned currents. Chapman and company, they denied their existence, but Alfvén and his group strongly favored the idea of Birkeland and in connection with the auroral images. But it required satellite measurements for uniquely determining the field-aligned currents. These became available in the 1960s. And it was one of the big sensations of the fall ACU 1975. It was a talk by Tom Potemra when he was showing his famous distribution of field-aligned currents. These two with upward and downward field-aligned currents. Actually, it was my first AGU meeting that I visited. And since then, I kept interest in the field-aligned current for the rest of my career. Yes, what is special about field-aligned currents? They play a big role in space plasma physics because they can connect largely separated regions in space, and they can transfer energy and momentum almost lossless over large distances. And this is because of the high conductivity of the field lines, and therefore they act as kind of equipotential lines, at least under DC conditions. If they are varying, then the things are different. But that means since all the magnetic fields in the magnetosphere are connected at least on one side to the ionosphere, any electric potential anywhere in the magnetosphere will drive currents in the ionosphere and dissipate energy here. Another interesting point is that field-aligned currents produce toroidal magnetic signatures, and these toroidal magnetic signatures do not contribute to the total field. So if you look at the total field, the field-aligned currents give no signature. Many of you have seen these cartoons before. We have a lot of different currents in the ionosphere. The ones of interest here are the field-aligned currents, which connect the magnetosphere with the ionosphere. Further out, we have the region 1 currents, which is connect to the outer magnetosphere, and the region 2 currents, they are at lower latitudes, they connect to the outer region of the ring current, and by that somehow map the dynamics from the magnetosphere to the ionosphere. Yes, what is driving the field-aligned currents? Generally, currents can be derived from the momentum equation, and that means the plasma pressure gradient is contributing, the ion inertia is contributing, and also the shear flow of the plasma is contributing. And in the MHD limits, this can the main contributors to currents perpendicular to the magnetic field. In the outer magnetosphere, the second term is mainly important, and it was shown convincingly by Johnson and Wings that the shear flow here near the low latitude boundary layer is mainly responsible for the region 1 field-aligned currents. In the inner magnetosphere, near the ring current, it's more the plasma pressure gradient that is driving or dominating the currents, and therefore they are more responsible for the region 2 field-aligned currents. For obtaining the field-aligned currents, you just have to compute the divergence of the perpendicular current, because you need a current continuity, and this continuity is made by the field-aligned currents. So this is the direct relation between them. But I don't want to go further into these details. Yes, now in more recent years, we have data from more reliable magnetic field data from recent missions like CHAMP and SWARM. And these have increased our understanding of the field-aligned current properties greatly. I will come to that later. We still have this standard loops of field-aligned currents, which are going downward here and upward here on the dust side, and vice versa, here upward, here and downward, the region 1 on the dawn side. And below the loop of field-aligned currents, we have the electrojet flowing in anti-sunward directions on both sides, here and here. But when we have northward IMF, interplanetary magnetic field, then these so-called cusp currents are showing up. Sometimes they are also called region zero currents, but I will talk more about these region zero currents later on. Here you see two examples of rather recent field-aligned current models, or maybe statistical patterns, and they are sorted by the IMF orientation. The top row, we have northward IMF. The bottom row, we have southward IMF. The left side is negative IMF BY, and the right, we have positive IMF BY. And what you can see, the clearest signature of field-aligned current distribution are obtained when we have negative IMF BZ. When we have positive IMF BZ, the shape looks a little bit different, and everything is closer to the pole. And we see also here additional currents, which are not so prominent in the other cases. Another recent model is from the group Edwards, Weimer and company. They come to rather similar results. They are using more or less the same data, so therefore it's maybe not a big surprise. What I should say here is what you see is the northern hemisphere distribution and for summer conditions. These are two important things to be remembered. In winter hemisphere, we do not have these NBZ current systems, and so on. Here I show again the situation for the northward IMF. If we have due northward IMF, then these two field-aligned current patches appear poleward of the cusp, and they are called the NBZ current system. This is merging poleward of the cusp, and they form here the loop directly above the cusp region. If the IMFBY is significant, then we get the so-called region zero current, field-aligned currents here, also poleward of the cusp. But in the case of negative IMFBY, this appears in the afternoon sector, and for positive IMFBY, it appears in the BY sector. But I have to say, all these features of the northward IMF change their polarity when you go to the southern hemisphere. So then this blue dot appears here, and so on and so on. This is opposed to the normal region 1 and region 2 currents, which do not switch polarity from north to south. Yes, you have to may think a little bit about why it is. It's because of the field directions are different in the southern hemisphere than in the northern hemisphere. Yes, these statistical patterns sorted by IMF and the tilt angle or the season, they provide a lot of interesting information, but there are also some limitations coming with these sorting of data. And these limitations are valid for all things which are not so closely controlled by the IMF. This is, for example, the latitude at which the field-aligned current reaches the ionosphere. Therefore, the peak values are distributed over a broad range. And that means the average shape of the field-aligned current distribution is flattened and broadened in these statistical models. Another point is the intensity of the region 2 field-aligned current is not so well controlled by the IMF. Therefore, these statistical models may provide unrealistic results. One example is, for example, the model of Edwards et al. They show stronger region 2 electric field-aligned currents on the dusk side than on the dawn side, but this is opposed to all experience and observation. Sorry, that's the wrong direction. And the third thing is there's a void of field-aligned currents on the night side when you look at these statistical distributions. This is because the substorms are not directly controlled by the IMF. Therefore, the pattern of the substorm field-aligned current is averaged out. So you have to keep these 3 points in mind when you look at these average distributions. Another possibility to avoid that is that you also look at the same time the equatorial electrojet. The electrojet is underneath the region 1 and region 2, and you can use the peak of the electrojet for normalizing the latitude of the different profiles. And if you do that, then you get nice shape of region 1 and region 2. Here is for the dusk, here is for the dawn. And then you also find that the region 2 current on the dawn side is larger than on the dusk side. And you find also that the rings, the distribution has a much narrower width and latitude than these other averages are showing. And also the amplitude comes out about twice as large as in the other cases. So this would be a possibility, is a possibility to improve these IMF patterns, but still you have the lack of activity here in the night side. This is also not healed by this approach. Now I come to the different scale ranges of the field-aligned currents. The field-aligned currents come at very different scales, and for investigating them, the swarm constellation is very useful. We have taken measurements at the same location, but at the same point. And the good location for that is the orbital crossover near the pole. And this crossover is passed by successive satellites at different times. Here is an example. For example, the red line is the swarm B. You see a huge small-scale field-aligned current up to 10 microamps per meter square. The ticks are 20 seconds apart. And 15 seconds later, the swarm A comes. It also sees this small scale, but much smaller amplitudes and shifted in time a little bit. Now, if you start to filter the data with a 5-second filter, 7, 9, and so on, the small scale field-aligned currents get smaller, smaller, smaller. And in the end, you just are left with a larger scale features, and they correlate very well. It's a little bit of time shift, but that's okay. And if you do this statistically, then you find that these small scales, let's say some 10 kilometers large scale, only correlate if the time difference is 10 seconds or less. All the rest doesn't give any good correlation. But if you filter things and go to larger scales, 50, 80 kilometers, then you get a good correlation even at 1 minute time difference. And if you go to the night side, this is even better than on the day side. So that means large-scale field line currents are stable for longer. Short-scale field line current are varying in time. They are not stable, and you need to sample them within 10 seconds if you want to see them. Yes, there had been similar investigations earlier by Ishii et al. Using DE2 satellite data, and they had the advantage of having electric field and magnetic field variations at the same time. And from the ratio of delta By over Ex, they could find that for small scale field line currents, the ratio approaches the Alfvén velocity. But when they started to filter the data and getting beyond 4-second cutoff periods, the value approached the Pedersen conductance. That means these large-scale field line currents here, they say more than 30 kilometer scale, they can be treated as quasi-static features, while the smaller things have to be treated as Alfvénic or kinetic Alfvén waves. And therefore, the swarm results agree very well with those which were found already earlier on. And we have to keep in mind that we have to treat the small-scale field line current as AC features, not as stationary. And this brings me already to the measurement techniques for field line currents. Typically, the magnetic field measurements from a satellite are used, and then they are taken into the Ampere's law. That is for the vertical component, dBy over dx minus dBx over dy. Unfortunately, if you have data only from one satellite, you only get magnetic field variations along the track. That means you have to simplify this equation. You have only the By component. So you take the delta By divided by delta t. That means the time variation of the measured By component, and multiply it by the velocity. This is replacing your dx. And of course, you have to assume that the dBx, the bx variation are unimportant. You can neglect them. Yes, that means you assume that all the By variations can be interpreted as spatial structures. This calls for 3 important assumptions. That means the field line currents have to be stationary for the time of passage. That means at least you have to suppress the Alfvénic wave. That means you have to filter them. Then the field line currents have to be organized in plane sheets. Otherwise, you cannot ignore the Bx. And third, the orientation of the sheet with respect to the flight direction has to be known and taken into account when you do that. Here is one example. You maybe fly at a certain angle through your pair of field line currents, and below the field line currents, you have your electrojet. What is commonly done is you apply the minimum variance analysis to the Bx and By component, and then find the angle. For this example here, this is from the St. Patrick's Day, for example. There's a very good linear relation between that both on the up leg and down leg, and you get a reliable magnetic field line current estimates from that. But there are other cases, and here is an example from a flight over in Canada. In that case, there was a strong substorm electrojet current flowing below the, and what you can see as a signature of this electrojet is in the vertical component, you see a bipolar variation. This is typical for flying over. And in the northward component, you see a strong positive bay. And here you have the eastward component, and unfortunately you get no good linear correlation between the two. That means in this case, the minimum variance analysis will not give you the proper orientation of the current sheet. You have a problem when you have these low flying satellites. If you have high flying satellites, 800 kilometers and more, the effect of the electrojet gets weaker and weaker. But these precise missions like Champion Swarm, they often encounter this problem. So therefore, it would be better to have more satellites to do the measurements of the field line currents. And then you can, if you have simultaneous measurements from more points, then you can use the ring integral over the magnetic field B times the path element dl. And then you have to divide it by the area and the permeability. You need at least 3 measurements at 3 points that you can do your ring integral. And when you have 4 satellites, you can build up 4 such triangles and then can calculate the full 3D current vector. You may think of cluster and MMS, which have these 4 satellites. But again, we have assumptions that means that, for example, the transfer scale of the field line currents has to be larger than the size of the triangle. If not, then you get spatial aliasing. Furthermore, the measurements have to be taken simultaneously within fractions of a second. And third, the magnetic field from one corner to the other may only vary linearly between the points. Again, otherwise you have a kind of aliasing. In the case of cluster, these 3 assumptions were often violated because of the large separations. Things are better in the case of MMS because they are closer together, but on the other hand, then the demands on the precision of the magnetic field measurements are higher because the closer the satellites, the smaller the signals, the more important is the noise. In the case of the swarm constellation, we take advantage of the 2 satellites which fly side by side in a configuration. And then we can build a quad of measurements. Here you have one satellite A, for example. It does a measurement here, and 5 seconds later, a measurement here. The same with a satellite C, measurement here, and 5 seconds here. And then you can do this Ampere's integral in a discrete form, like shown here. The 5 seconds is equal to 38 kilometers because of the satellite velocity. And the cross-stack separation is 1.4 degrees in longitude, which is about 50 kilometers at 70 degrees latitude. And then what you get is a vertical current, JZ, mean vertical current flowing through this area. And by projecting this vertical current onto the field line, you get the field line current. Again, we have some assumptions The horizontal scale of the field line current must be larger than the quad size. Again, as said before, the stationarity of the field line current must be longer than 5 seconds or a time shift. And the field change between the points must be linear. This is as before. Yes, and for satisfying the 1 and the 2, we are applying a 20-second low-pass filter to the data. So that means all the small stuff is ironed out. But on the other hand, that means our results are limited to scale sizes of 150 kilometers and longer. Here you see few examples. Normally, when we fly through the auroral oval, and you see here the results from the single satellites, A and C, B, yeah, and the dual solution, and all three match very well. That's normally the case. But we have also cases here where we have clear discrepancies. And normally, the dual satellite results are larger. Here's another case. But interestingly, these discrepancies show up normally at higher latitudes, so more in the polar cap regions. We have tried to check which of the two solutions are better. And here we do a comparison with the DMSP. The DMSP on one hand gives an auroral image. You see here the swarm flying through the image, and you can clearly see here it is flying more or less parallel to the oval, and that means the single satellite has no chance to come with a good result. And that's what you see here. It is fitting reasonably well, but then it gets worse and worse. We also compared it with the precipitating particles. And what is nice to see, whenever we have upward field line currents, which is the negative here, then we get electron precipitation, burst of electron precipitation, and also the ions fluxes are high. So these results show that the dual satellite approach does a good job, even if, because it doesn't care about the alignment between track and the orientation of the sheet. Then the other thing is the Ampere project that has 60 iridium satellites in 6 different orbits, and data sets of 10 seconds are taken together. Here you see an example of measurements. It's not so clear, but it is not so important here. What these people are doing is they take measurements from 10 minutes and then smooth the electric field readings with the help of spherical harmonical cap analysis. Then they get this nicer magnetic field deflection distribution. And on this distribution, you can then apply the curl of B to derive the vertical, sorry, to derive the vertical field line, field curl. But many of our assumptions that I introduced before are violated by that. Separation of the spacecraft is too large. They are 30 degrees separated by each other, so much larger than the size of the field line currents. And the measurements are not simultaneously. But still, they obtain reasonable results. Look here, and when you compare it with this Ijima-Potemra pattern, you can find things again. So what is the magic of this? The answer is there is a persistent pattern of field line currents, and the Ampere measurements mainly reproduce this pattern because it's there all the time, and therefore it doesn't matter whether you come at which time you come, you will always find this pattern. And therefore the ampere is, in my eyes, more or less rescaling the Ijima-Potemra pattern every 10 minutes. And by that, it's tracking the IMF and activity variation, but details are smoothed out because these details are not persistent. It's just the persistent part that is reproduced. Here for the St. Patrick's Day, for example, we did a direct comparison. Here you see the swarm flying through the ampere pattern. And it's nice to see. You see, it's upward here, like here, downward here, and then comes upward again, and so on. And so on the other side, downward here, upward there. And a little later, you find also the same thing. Upward here, then downward, then upward, and so on. But on the other hand, swarm is finding or reporting peak amplitudes of 3 microamps per square meter, and ampere is more like half of it, 1.5. So the large scale features are well represented, but things are a little bit smeared out, and the amplitudes are reduced by a factor of 2. So it depends what you are interested in. You should know what you get when you are applying the ampere data. Here a little commercial. In the last years, we had an easy workshop, and in that, the details of field line current estimates were discussed and resulted in a book. So this book is freely available, and you can download it here if you're interested. But this just as a short advertise for that. Now, let me come to the field line currents of magnetic storms. The example I'm showing here is from November 2003. That was a superstorm with a big DST going down to almost 500 nanotesla. You see the passage of a solar magnetic flux tube, a typical signature of the BY changing sinusoidal, and the BZ is changing 90 degrees shifted to that. Interestingly, there is no simple relation between the solar wind input and the intensity of the field line currents. When you see here the field intensity of the field line currents, and here is a BZ component, you see you have a very large here in the beginning and large more in the end. But interestingly, if you compare the dynamic pressure with the intensity of the field line currents, then you get a much better correlation. And this is something that was already mentioned by Ramon Lopez in his presentation, that the dynamic pressure also has influence on the field line currents. Furthermore, we see that the field line currents are in the southern summer hemisphere are larger than in the northern hemisphere. This is because of the conductivity in the summer. Another thing is the latitudinal variation of the field line current during the storm. And what we find is that the latitude of the field line current follows quite nicely the amplitude of the IMF BZ, at least as long as it is negative. In the southern hemisphere, better than in the northern hemisphere, it's reaching a saturation level at a certain point. And this certain point is on the night side. On the other side, it follows more the evolution of the DST. And this means the equatorward expansion on the night side is about 1 hour delayed compared to the day side. You can say this is just a single swallow that doesn't make a summer, but we can go to another Substorm, which is more complicated. But again, we find this nice tracking of the latitude by the or following the VZ amplitude with a latitudinal expansion, and also here in this one. Again, here on the night side, it's more following the DST. So that seems to be a quite common thing, that the latitudinal variation on the day side is tracking more the BZ component. And here you see the linear correlation. It's quite a nice linear correlation. And you get, at a certain level, you get a saturation. Interestingly, the slope is the same on the northern and in the southern hemisphere. And it's also the same for other storms. But the level of saturation is different in the two hemispheres. It appears at higher latitudes in the winter hemisphere than in the summer hemisphere, but that is a well-documented effect. It has nothing to do with the sunshine, it has more to do with the tilt angle. But on the other hand, this saturation level is also dependent on the prevailing dynamic pressure. If the dynamic pressure is higher, then this saturation level will show up at the lower latitude. I showed the day and night side, but you also have on the flanks, you have also the linear decrease on the flanks. The flanks, you have the intensity of the field line current is rising with this input of the solar wind, but it seems to level off towards higher merging electric fields. But that would have needed to, we would have to look into that closer. I have no answer for that. Now I come to the substorm. There are complex field line currents involved with the substorms. And the onset is typically defined by the collapse of the neutral sheet current, and part of the current is then rerouted through the ionosphere. Already Substorm suggested, well before he had satellite measurements of the field line currents, that there should be two types of field aligned currents. There could be two types of field line currents, and he called them type 1. That is this one where you have this kind of current wedge situation, and here the closure between the field line current would then be by Peterson current. Or he said there could be two sheets of field line current. One is further in at lower latitude, and the other further out on higher latitude, and then the substorm electrojet would be a whole current. Yes, nowadays we know that both types of Substorm field line currents are active. At the start of the substorm, you have the plasma coming in from the tail, and then it is diverted to the flanks, and this shear flow is producing field line currents, which are inward further out and back further in. That means they form the type 2 Substorm field current, and they set up an electric field here that can drive Hall currents. But this Hall current, or this current which is needed to close the current wedge, is too strong for the electric field. So therefore, it needs a higher conductivity. And obviously, there is a kind of cowling channel forming, and this cowling channel is able to carry this very high current. And therefore, in addition to the type 2 field line current system, we also have the type 1 field line current system, which is supported by this high conductivity in the region. Nowhere in the Oro region you find such a huge, let's see, electrojet compared to the strength of the field line current as here around the substorm current wedge. But this is still under debate, this whole story. Now let me come to my last point. This is the character of small-scale field line current. And as I said, I'm quite excited about them. When you look at a field line current measurement from swarm here, again, you have the three solutions. This is for things larger than 150 kilometer. Amplitudes are typically 1 microamp per square meter. But now you go to higher resolution, 10 kilometer to 150 kilometer, and then you see the amplitudes are getting larger. You have at least 5 times larger peak amplitudes. But now you can go even a step further and you say, I go down to 1 kilometer. And then you see amplitudes surpassing 100 microamps per square meter. So really huge amplitudes. So the smaller the scales, the larger the amplitudes. And already years ago, Tom Potemra once asked me, is there a smaller scale of field line current? We made use of the CHAMP high resolution data, 50 Hertz, looking into that. And here you see an example of such a high amplitude, small scale field line current. If you are running a spectrum over this event, then you get a flat spectrum up to a certain point, 8 Hertz, and then a steep drop off. So this part of the spectrum is resembling a delta function. But if you have a delta function with finite widths of the peaks, then you get a roll off. And that means our 8 Hertz corresponds to 1 kilometer scales when we take into the 7.6 kilometers per second of the satellite into account. We have tried the same spectrum analysis to many of such events, and then you get a mean spectrum and it follows the same shape. Also here is around 8 Hertz, this knee. So that means obviously field line currents with 1 kilometer size have the largest amplitudes. This is the answer to Tom Potemra. And this result was also supported by a recent consideration study by Lotko and Zhang. They find that the finite conductivity of the F region damps off the smaller scales, and therefore these things cannot grow any further. Yes, why are these small scales of interest? When you have a storm, then the field line currents are heating the upper atmosphere at the poles. And that means atmosphere is going up, and the enhanced, the bulge of neutral atmosphere is propagating equatorward from both sides. And this goes with a velocity of 600 meters per second. CHAMP was the first satellite that was able to give a systematic measurement of the thermospheric density. And it turned out that the thermospheric density is a wonderful medium for detecting the energy dumped into the upper atmosphere. It works like kind of a black body, regardless in which wavelengths and in which scale size and so on. The very interesting thing was when we were flying around, the accelerometer gives us the orbital variation. That means on the night side, the drag is low, on the day side, the drag is high. But on the day side, you find narrow peaks. That means local density enhancements. And they are all collocated with a cusp. This is the region where you can funnel a lot of energy into a small point here. When we look closer into these events, we found that we always have high amplitude, small scale field aligned current coinciding with these local density enhancements. And the point is, when you are averaging the magnetic field data first, then you lose the information about the small scale field aligned currents. But the small scale field aligned currents, they are also important for the energy dissipation, because in this equation, the small scale do not average out. You are squaring the things. And the interesting thing is the location where most of this upwelling takes place is in the interface between the region 1 and region 0. And this is here the negative Vy on the afternoon part, and here for positive in the pre-noon part. Yes, Lotko and Zhang, they have also looked into this business, and they find that the energy deposition of small scale field aligned currents, which have alphanic character, is in the F region. And the DC, the large scale field aligned current, they deposit everything more or less in the E region. But here in this region, the air density is lower, and so you need less energy to produce large temperature. And this large temperature is driving up the air to the high altitudes. And therefore, these small scale field aligned currents correlate quite well with the air density at satellite altitude. Here you see, for example, a statistic of density anomalies. Clearly, the cusp region is very prominent. Here is the small scale field aligned current intensity, also cusp region, very prominent. Also a little bit here in the substorm region. But look here on the dawn side, you see a depletion of density, and also a little bit on the dusk side. Compare that with these statistical magnetic field aligned current. You have the highest field aligned currents here on the dawn side, but this is large scale field aligned currents. So therefore, this enhancement here is taken away here and here. So therefore, I think the small scale field aligned current are very interesting and very important. But they are quite difficult to measure. Therefore, we would need both E field and B field at the same time. Otherwise, we cannot characterize them properly. Furthermore, these small scale field aligned currents are very important for heating the upper atmosphere, and the resulting air densities are affecting the satellite orbits. Therefore, they are of interest there. The large scale field aligned currents, they are more important for the momentum transfer. So therefore, they are controlling the plasma convection patterns. Here I come to the summary, but maybe I should stop here because I have used up my time, and you can read it, and maybe you have questions.
Good. Thank you very much, Hermann. I will give people a few moments to read this before we move on to questions. We have some very interesting questions here, but we just pause for a few moments in case anyone wants to check this. Of course, the talk is being recorded and it will be posted on YouTube and posted on our website for those who are looking at this final slide. I'll just pause.
Yes, in the end, you see my outstanding issue, small scale current, small scale flux.
I see, and that certainly is fascinating. Okay, we do, thank you again. We do have some very interesting questions here. Let's go back, we'll take them sequentially. So in some way, there's some correspondence between the sequence of these questions and the order of your presentation, because they came up as we went along. The first one is from Harold Frey, And perhaps you can go back to a slide where you showed the location of field-aligned currents as a function of IMF BY. That would be early in the presentation. And Harold
Yes.
says he was surprised because it was his impression that cusp field-aligned currents shift to pre-noon for negative BY in the northern hemisphere and for positive BY in the southern hemisphere. What can you comment about your patterns and that impression?
Yeah, well, sorry. Yeah, I should have read the Londal paper, maybe because more to interpret his colors correctly. Yeah, we have here the red, as I see here, the red are the upward field aligned currents. This is well known, the region 1.
Yeah.
And yeah, and this is downward field aligned current, the blue here. So I only can show, this is not my work, this is a work from Londal and others. And therefore, he probably should pass his question further to Carl Londal.
Okay.
Because I just show it here. But in principle, I see here the Edward Weimer also has this other pattern here.
Okay.
So yeah, I hope I haven't taken the wrong hemisphere. Yeah, sorry, I cannot answer that because it could well be that I took the wrong hemisphere.
All right, we leave that for further investigation. Okay, the next question, there's a pair of short questions from Ankush Bhaskar, and he's curious about the orientation of field-aligned current sheets. Does the IMF determine their orientation at any given local time?
Yes, sorry, this is the wrong direction. If we have northward IMF, then the IMF, the BY is determining whether we have prominent region 0 current flowing out or flowing in, or if we have the negative, we have the opposite direction. But sorry, this is again the same confusion here, but you see the direction of the IMF BY is determining the direction of the field line current forward of the cusp.
But his question is the orientation. You mentioned people use minimum variance routines.
Oh, I see. Yes. Sorry. Now then I misunderstood it. Yes. Yes. No. The point is the electrojet. Yeah, no, it's not. The electrojet is only disturbing the determination. It's not disturbing the orientation.
Okay. All right.
I think this large configuration is not changed by the IMF-BY. It is just this cusp currents which are determined by the IMF-BY, but not the big ones.
Okay. The next part of it, the second part of his question, is there any evidence for the field line current pattern to exhibit a twist? I think perhaps that might to be filamentary or to not be planar.
Oh yes, this is, I could have shown an example where you see a nice circular pattern and where the minimum variance has no chance.
Yes.
But I had no time.
Okay, thank you. The next question is from Sergei Apatenkov, and he's interested if it really is possible to detect the electrojet from low altitude spacecraft at 500 kilometers. Would it then be possible to determine Pedersen and Hall conductances from observations, perhaps over a Cowan channel?
Yes, in principle, yes.
Okay.
Yeah, we haven't done that. We have tried that in the simple areas at the dawn and dusk, where you have a nice a large-scale configuration, but we haven't tried it in the polar region. But that is an interesting point, I must say. Yes, it should be possible.
Okay, excellent. Next question is from Eric Lunt, and he noted that you said that the night side field-aligned current latitude, it depends strongly on DST. Is there a physical way he can understand that, why it should be that the latitude of the night side FAC should depend on DST?
Yeah, this is an old story already. When Birkeland was doing his experiments, he found out that his auroral oval is too far north or too far, close to the poles. And then he asked a theoretician, Stürmer, and he said, you need a ring current to move the auroral oval further to the equator. So the ring current directly is moving the auroral oval. The magnetic field of the ring current is causing the equatorward motion of the auroral oval. And this works on the night side, but on the day side, of course, you have other sources for the field line currents.
Good. Next question is from Lisa Antonova. Is it possible to select field-aligned currents producing individual inverted V auroral structure features using swarm observations?
Ooh. I don't know, but unfortunately, Swarm has no particle detectors on board. We were proposing those, but they were cut off. Yeah, it's I cannot say so, but I mean these nice swarm field line currents, they are the larger scales, 150 kilometers. And when we come to smaller scales, we have to go back to the poor single satellite. So I'm not sure whether this is possible. Sorry, I cannot tell.
Good. Next question is from Drew Turner, and he, like you, is very interested in these small scale currents, 1 kilometer scale size currents. And he would like you to imagine extending them out into the magnetosphere. How far should you extend them? All the way to the magnetotail plasma sheet? What would they map to there? Where do they go? Where do they come from, is his question.
Okay. Yeah, probably not. The common theory is that this filamentation of the field line current comes at some Earth radii, maybe 2 or 3 Earth radii altitude, where the current density becomes critical, and then the nice larger scale field line current is splitting up. So I'm afraid you cannot use this small scale field line current for mapping. That is the difficult thing. So there is this acceleration region at 1 or 2 or 3 Earth radii high, where this filamentation.
Okay, just one double question and one comment. The double question is from Ankush Bhaskar again, and he'd like you to summarize as a function of scale size, what do you think the underlying mechanism is for field line currents? What do you think causes little tiny ones at 1 kilometer, and what causes the global one? I guess he'd like to fix that idea. What processes correspond to small features and which to big?
Yeah, these larger scales probably are directly generated in the magnetosphere, like by shear flow or pressure gradients and things like that. And if you only look at the DC part, 1 minute or longer period, then you get very good mapping of that. But in reality, when you really look at the raw data, you just see this. You have no glue of this field line current. These large scale field line current are really buried in 100 times larger small scale stuff. And only by averaging that, there is a small uneven distribution. So this is what people do not realize, that in the raw data shows this. And when I did my rocket experiments as PhD student, I only saw this kind of field line current. I was so disappointed I couldn't find the E.g. Maputembra pattern. But now I know this is actually how it looks.
Okay.
So everything is split into little parts in this acceleration region. Yeah, sorry for that, but
no, that's good. So the second part of his question is closely related. He'd like to know whether he should understand the small scale structures as a kind of end product of large scale structures, evidence that they're dissipating and breaking up into small scale features.
Yes, that's true. It's the large scales are breaking up into the. When you compare, for example, cluster or other magnetospheric satellites with swarm or SMIT, then the large scale things fit reasonably well, but the small scales, of course, not, because this generation or this cutting into pieces becomes in between the field lines.
Okay, and the last comment has just become a comment and a question by a supplement text message. Pat Reif notes that when she looked at DE1 and DE2, she found that current systems extended up to 15,000 kilometers. And she wonders if anyone has done more work on that region of space, trying to map upward from the low altitude spacecraft into kind of middle Earth orbit regions recently.
Yeah, good question. I only know examples from the outer magnetosphere, from the tail to the auroral region, where you can find reasonably well correlations, even the PI2 position and things like that, but not from the middle so far. There was this fast satellite mission, and they were designed for doing measurement in the acceleration region, where the splitting of the field line current takes place. I think that is probably the mission which is closest to the question of Patricia.
Okay, thank you again, Professor Lüehr. This was a very clear, remarkably wonderful seminar. I'd like to thank everyone for joining us and for the many interesting questions we had. Next week, at the same time and in the same place, we'll hear from Bill Peterson about ionospheric outflow. Looking forward to having everyone with us again in a week. Thank you again, Professor Lüehr. Bye-bye.
Okay, thank you also.